Welcome everyone. My name is Anne Livingston and I will be the chair and moderator for today's webinar for the Community Care Smart Assistive Technology Collaborative. Our webinar today is Harnessing Technology to Improve How Children with Cerebral Palsy Use Their Hands. This webinar is part of a series being facilitated by Community Resourcing for the Community Care Smart Assistive Technology Collaborative. At Community Resourcing, we use our international expertise and networks to build community capacity through empowerment, knowledge transfer, skills enhancement, and importantly, research and development projects. Community Resourcing has been funded by the Queensland Government to bring together an online platform for community service providers who are interested in collaborating on issues and practices related to smart assistive technology. We're really honoured to have been awarded the ICT Innovative Entrepreneurial Award at last year's ITAC conference for this project, and also several members of our reference group have been recognised in the Advanced Queensland Community Digital Champions program. Today's session has been oversubscribed, indicating a high level of interest in incorporating innovation into practice and particularly this subject matter. As attendees at today's session, and in the interests of recording, we have muted your microphones. But if you have any questions, and we'd love to take your questions, please add these to the question pane. The question pane is on your dashboard to the right of your screen, and there will be an opportunity at the end of today's session to have these answered. The session is a continuation of webinars being held by the Community Care Smart Assistive Technology Collaborative. We're trying to bring you a range of subject matters and detail a range of technologies that can provide assistance. But please note that neither Community Resourcing or the Department of Community, Child Safety and Disability Services are promoting or endorsing any particular product, research entity or organisations. Our webinars serve to inform viewers of examples of various smart assistive technologies in development or in deployment in community care. We're really pleased to have today a world-leading researcher, David Hobbs from Flinders University. In today's session, David will discuss some of his research projects around how gaming technology is improving and driving improvements in the use of hands of children, in particular those with cerebral palsy. David is highly qualified to deliver this program. He has bachelor degrees in physics and biomedical engineering with first-class honours from Flinders University. He also has extensive experience as a rehabilitation engineer in the field of disability, rehabilitation engineering and assistive technologies. And he has also worked at Novita Children's Services in a variety of technical and management roles for over 9 years. One of David's key achievements while at Novita was the Australian commercialisation of a novel software program from Canada that enabled children with disabilities to play music simply by moving. David is currently a lecturer and academic staff member with the Medical Device Research Institute at Flinders University in Adelaide. We recently had the opportunity to visit with David and his colleagues, and I'd highly recommend the Institute to anyone considering research links in this area. He's also in his spare time studying for his PhD, which is in the area of development of a novel computer game intervention for children with cerebral palsy, and particularly a focus on improving their hand function. David's professional honours to date have included a Churchill Fellowship in 2003, Engineers Australia Young Professional Engineer of the Year in the next year, 2004, and Engineers Australia Top 100 Most Influential Engineers in 2005. Recently in 2008 he was also provided with a Fulbright Professional Scholarship and in the field of paediatric rehabilitation engineering. As well as all those awards, David has extensive experience in working in rehabilitation engineering research and industry institutions across a number of countries, including England, Canada, United States, and here in Australia. I'll welcome David to today's presentation.
Thank you very much. That was a fantastic introduction. And first of all, can I begin by thanking Community Resourcing and Anne and Elizabeth for all of the support and help in getting today happening with the webinar. So thank you very much for your help as well. So today I'm going to be giving this presentation on how we've developed this novel gaming system to effectively harness the motivational aspects of engagement with children with cerebral palsy to use their hands. And as you can see from my title slide here, I'd just like to acknowledge my supervisors for the project, so Professor Karen Reynolds, Associate Professor Ray Russo, who's a rehabilitation consultant at the Women's and Children's Hospital here in Adelaide, and Associate Professor Susan Hillier, who some of you may know from the University of South Australia. And just recognise that this sort of project has had a number of professionals working together, and you'll see some of the aspects of that coming through today, but that it's been a collaborative project from Flinders University, the University of South Australia, and the Women's and Children's Hospital. So what I'm going to do today is give you a bit of an overview of the project and talk to you about cerebral palsy and how we designed what we designed, and then I'd love to take some questions and comments towards the end on what we've done, and look forward to any feedback that you have. So I suppose before we get any further, for those of you that are not intimate to the field of, say, cerebral palsy or disability, cerebral palsy is the most common form of physical disability in the world, and here in Australia we know that a child is born with cerebral palsy every 15 hours. The prevalence of cerebral palsy here in Australia is roughly 2.2 to 2.3 live births per 1,000 births, actually per 1,000 live births, which is fairly similar to what it is in the United States and Europe. And globally there's more than 17 million people around the world who live with cerebral palsy. At this point in time there is no cure for cerebral palsy, but I know that there's some fantastic research going on in New South Wales at the Cerebral Palsy Alliance that is looking to finding a cure for cerebral palsy, which is extremely exciting. So typically if someone does have cerebral palsy, it is classified as shown in this figure here. So we say that someone tends to have diaplegia or hemiplegia or quadriplegia from a one type of classification system. And you can see here that the different colorings of the individual standing there is showing you how that person's motor function is affected. More affected in the legs with these photos, but the hand and the arms are always affected as well. What many people don't realise, but this is actually coming more to the fore nowadays, is that someone with cerebral palsy, particularly children, actually has what we call a tactile sensory deficit in their hands as well. And what that actually means is they don't sense touch in the same way that an able-bodied, typically developing child senses touch. And so that's what this image here is trying to show in terms of the child holding the mother's hand, that the sense of touch is not the same or not what it should be. What we also know from our research here in Adelaide, from research which has been conducted by Dr. Megan Auld in Queensland and from other research groups around the world, is that this impairment in sensory function is not just limited to the side that's what we say more involved. So if you have a look at that middle person in the figure on the left, they're showing that one side of the person's body is affected with hemiplegia. In that figure, just that person's right-hand side. We know that that might be what the motor impairment is, but the sensory impairment is actually on both sides, and it's not something which is generally well known. I like to show this image here because the key messages that we can take away from a photo like this or the images like this is that all those children are very intensely engaged in what they're doing. If you have a look at the eyes, the focus, their attention, what they're doing is they're totally immersed in the activity. And as that figure in the bottom row in the middle shows, some children, particularly probably when they're not at school, literally may eat, sleep and game, and that's all they do. And as a parent of 3 young children, my kids aren't at that stage yet, but when they are, we might have to be turning the gaming system off or putting some parental controls around how they use it just so they get outside and play and run and jump and climb trees like I did when I was a child. But as the title says, computer games are great, but we know that if a child has an impairment in their hands, and if that impairment is due to cerebral palsy, we know that they can't engage and play off-the-shelf computer games just like those images we're showing. And so we say that these children are excluded from doing this because of their ability to, or their lack of ability to control their hands. So the control, the coordination, the dexterity, the manipulation, the fine motor control of fingers and thumbs to use the controller and to press the buttons. We also know that children with an impairment have to do therapy. It's part of the work that they have to do, but that's the problem. It's viewed as work, and because therapy is viewed as work, it may not be engaged with or done as much as therapists and others would want it to be done. So engagement and motivation really is the key. And if you've never heard the term serious games, hence the title, Are You Serious? Well, it's actually a term for a suite or a collection of computer or video games where the games are for more than just entertainment. So if I was to turn on a gaming system and play it, my goal would be some escape from the real world to try and get a high score and to try and beat the people I'm playing with. But if you drop that game into a management context, in terms of management training or education or in health gaming, then it becomes a serious game because it's being used for other purposes. But as I highlighted before, we have this inaccessibility issue. So shown on the left, we have a Xbox 360 controller, if you're not familiar with those, and on the right we have a popular game, I think that's Guitar Hero being shown there. But the problem is that it's not one of those items which is causing the inaccessibility. The controller on the left requires fine motor control, dexterity, coordination. You have to hit those colored buttons which you can see near the right thumb. You might not be aware, but that controller that's being held in that person's hands there has about 15 different buttons. You use 4 to 8 of them in most games, including the thumbsticks. You can see the 2 thumbs are sitting on top of thumbsticks, but it requires a lot of fine motor control. But on the right-hand side, from the game perspective, the game expects all of those inputs from the controller on the left-hand side. And so it's not just a case of being able to access one button or 2 buttons if you can. It means you need to get access to all of the buttons. The other aspect with the games is they require what we call a temporal response. So you have to hit a certain button at a certain point in time, or else you can't jump your character or fire a torpedo in a certain direction or do something like that. So together they actually reinforce the inaccessible aspects of each other. The controller and all of its buttons is reinforced by the fact that you need access to lots of buttons in the software, and the software, because it requires you to hit buttons at certain times and in certain orders, reinforces the inaccessibility of the controller. So we have 2 problems. Most people, if they're looking at game accessibility, will try and focus on one of the issues. Develop customized software so that the software does not reinforce inaccessible issues, or develop custom hardware. But what we decided to do was to tackle both issues. We decided to look at both the controller and the hardware, so the hardware and the software. So it was about developing a controller that children could use, interact with, but they thought was cool, combined with an interactive, commercial quality set of computer gaming software, so a hardware and a software solution. Now, when at Flinders University here in Adelaide, when I teach engineering design to first-year students, and one of the things we talk about is that you can't really go into a design challenge or a problem with a preconceived idea of what the output is going to be like. You have to approach it from a solution-neutral perspective by, first of all, understanding the problem, having empathy with the people that are part of the problem you're trying to solve, and then looking at it from their perspective, but also from a simple requirements perspective. What does the person want to do? How can we facilitate or maximize that opportunity? And so I want to just reinforce that from a design perspective, we use that universal design or inclusive design approach to not start with what we thought might be the outcome, but just what we knew would hopefully solve the problem. So this is one of the problems that we tried to address, and this is an Xbox 360 controller, and immediately you can see those 4 color buttons which are used in every game. You can see the circular button in the middle. I might be able to use my mouse here. The circular button with the X on it, that's actually a button. There's 2 small buttons here, and from a universal design perspective we'd say that they're very poor because the contrast is very poor. The 2 thumbsticks here and here, and then we can see the D-pad here. But there's also buttons along the top and underneath the controller as well. So we had to rethink how this was working as a controller. To do this, I actually had 4 students from the Industrial Design School at the University of South Australia work with me on what their concept of a novel controller could be. And then I had 2 students actually work with me at a much deeper level. So I'm going to present to you today the 2 students' outcomes and the work that we had to come up with this accessible controller. So everything starts with an ideation process. And so today, with this particular example, the ideation process was taking away the ability or the need for fine motor control. So if you have a look at these sketches, which are here to help that ideation process move forward, except for the one in the middle, which has got a bit of a H look to it. I'm sort of moving my mouse over it now. They don't require grip or fine motor control. This one here on the right requires you effectively just to put 2 hands on a slab or a flat square here, and then you move your hands backwards and forwards. This one here requires you to put your hands on top of this sphere or orb-shaped aspect of the controller. And effectively, all we're asking the person to do is move the controller forward, back, left or right. So it's just a rotation around the wrists. It's not requiring button presses. What we ended up coming up with, and just to show you that that was just one aspect of ideation, was these 2 controllers here. So shown on the left, starting at the top, one of the industrial designers took the approach that if we could just get them to put their hands on 2 curved objects, and if we can reinforce the fact that we're using computer technology, and so they took a mouse approach, so these look like mice. And then on this particular device, you move the green plate forward, backward, left and right, and it just moves on top of that circular circular base, the white base here. The bottom controller here picks up on that sphere or orb-looking controller from before. You can see it's got a wide base as well, and effectively you put your hands on the controller and you rotate it around to use it as you need to control it. I just want to highlight that both of these controllers have this red button here. You can see it on this controller here, and what we call this is an out-of-game button. So the requirement for the controller was you didn't use any buttons when you were in the game. You just focused on controlling the character in the game by moving the joystick effectively forward, back, left and right, and rotating or moving it around. But when you want to select a game outside of the game, you would use these buttons to actually select the game. This was a 12-week process to go from nothing to this, and we actually had working prototypes. And so the arrow and the question mark on the right-hand side show that, well, we did this whole process again over another year, and then what did we come up with? What eventuated for one of the controllers was this, and we called this the Orbi controller, and you can see that Max Hughes was the designer who worked on this particular controller. So we actually have the prototype controller of this here in the building, and from a design perspective, this controller met the brief that we had for the controller very, very well. The reasons for that was it didn't require any fine motor control. You effectively put your hands on these oval pads that are shown in grey here, and you controlled the controller in doing so. We had a big red button out the front for the external button to hit this button to select games and things like that in the menu screen. We're providing a strap here in case someone's hand just needs to be held on the surface of the controller. So if they didn't quite have the manipulation and control, they could just rest on the side of the sphere and the strap would hold it on. And it meant that we didn't have to incorporate in-game buttons, and it had both hands being used at the same time. The aspect here was sensory stimulation that I'm showing in the middle, and the arrows is because both of these controllers, in fact the requirement for the controller was that it needed to provide vibration or haptic feedback to the user. So when they played their game, if they did something in the game that would be resonated with in terms of a vibration, feedback, a mechanical feedback, then that occurred via the controller. So if they collected a bonus, or if they were driving a car and they accidentally hit the wall, they get a vibration on their hand. And that was very important because we were trying to reinforce haptic or vibration feedback on their hands, because if you remember right back to the slide I talked about with cerebral palsy, we know that most children actually have an impaired sensory function. So we're trying to send afferent stimulation to this hand, which is more involved, the hand which does not sense touch in the same way that a typically developing child's hand does. So from a first prototype perspective, we ticked a lot of boxes with these, with this particular controller. The second student working with me came up with this controller. So you can see that this one here has morphed quite a bit from what the original design he had with the mice sort of sitting to the side of a green plate on top of a round base. It's the same idea. You use this blue base to move the controller forward and backwards, so forward, backward, left and right. And you can see it's all the same things that we were talking about before. So we have an external button in a place or a location, which is easy to get to, a restraint strap in case the child's hand needs to be just held on top of the controller. And you effectively slid this base. So this was a sliding mechanism where you slid the top with reference to the bottom to control your character. So again, it had both hands on the controller. It gave haptic feedback to the child's hands as they were using the controller. And there was no in-game button, just this red out-of-game button as well. And this is the design Tom came up with. We put both of these controllers through a focus group with teenagers with cerebral palsy, and it was really quite an amazing and enlightening experience to see these two teenagers use and interact and make comment on the controllers. And in the end, the controller we went with was this one here. And the reason we did this was because this controller ended up being more intuitive to use for the player. So they instantly would sit in front of it, they'd put their hands on the controller, and in doing so they had an instant appeal, but also an instant connection to using the controller in the way we wanted them to use it when they played the games. One of the drawbacks of the previous controller was because it worked in a planar fashion, so the top plate moved with respect to the bottom plate. This meant that when they were playing a 3D game and they were immersed in the game activity, they tried to lift the bottom plate. So they actually tried to pull the blue plate off the white base, and that wasn't successful. So this ended up being the more intuitive controller. So that controller again went through a process of redesign and design iteration to end up with what we actually now call the Orbi controller. You can see here, it's sitting in front of our gaming system, which I'll talk about in a moment. So it's the sort of sphere or orb shape. The grey oval pads here indicate where you are to put your hands to play the games. If I click again, one of the aspects I've already highlighted is that my PhD was looking at improving sensory function in the hands of these children. So you can see this grey pad is actually textured here, so they get a textured feedback when they put their hands on the controller. And we have this little tiny hole in the oval pad here, and this is very, very important. The reason we have this little hole here is because we have little smart sensors placed beneath the surface of the controller. And these smart sensors are continually looking for children's hands over those oval holes. And if the hands are over the holes and covering them, the system will play the computer game. But if the child's hand is not covering the smart sensors, it will pause the video game, and I'll show you how that works later on. And what we discovered was that this idea of having these children use both of their hands, so their more involved hand and their hand which is not more involved with the cerebral palsy, both of these hands on the controller, those smart sensors were very pivotal in having them place both the hands in the correct position. When you plug the system in, it also shows you with visual feedback that it's turned on and ready to use with green LEDs which show up around the rim of the bottom here. So our final controller here, if you're into some advanced manufacturing, has also been 3D printed. So everything you can see on this controller except for the acrylic base, which has been laser cut on the bottom, is actually being 3D printed locally here in Adelaide, which also gives it a bit of texture, and you might be able to pick up on some of that texture around the oval pad with the photo here as well. So our physical prototypes for the controller, which we still actually have here in the building, move from left to right here. So our original controller, which was where the idea came from to use this sphere or orb form for the controller, The controller we prototyped in focus groups to get feedback and critique from children with cerebral palsy, and then our final trial controller, which we used for the randomized controlled trial for my PhD, which was 3D printed. So this one here on the right hand side is the only one that was 3D printed. The rest were manufactured using traditional purposes. And you can see they have a very similar form, but from a technical perspective, under the hood, so to speak, there's differences in each of them to do what we would like them to do and for the children to use them in the way we'd like them to use them. All of them still function and work, so if I was to plug all of them into our gaming system, they'd still work. So that was how we designed, and that was the methodology we took into developing our controller. So a bimanual device which removed the need for grip, fine motor control, didn't require buttons to play the games, and meant that they could effectively put their hands on the controller and just control their character in the game. On the other side of the fence, the other half of the project was developing what we call the rehab games for the project. We opted to design our own games from the ground up, and I'll explain why that was the case rather than trying to use commercial games. But effectively the mantra or the guidelines that we use for developing the games was that they could be any game you wanted to make from any genre that you liked or you had an affinity for, as long as they only required joystick motion, hence the four-headed arrow in red on the right hand side. So as long as your game only required the person who was using it to move a joystick in those directions and it didn't have any in-game buttons, well then that was probably going to be an appropriate game for us to use for this particular trial. The subcategories or the sub-guidelines we used after that, and I apologize for the amount of text on this slide, but the communication here is just trying to say that we were using appealing colors, sound, animation, and also challenging gameplay. Most of you, if you sat down in front of a game, one of the reasons you'll probably go back to play that game again is because it engaged you or challenged you in some way. If a game is too easy, you probably won't play it again because you feel you can master it or have mastered it. So challenging gameplay was important. The single most important aspect of the PhD research I was doing, though, was to look at this idea of afferent sensory stimulation to the child's palms and fingers when they played the games. So that's why we textured the oval pad for the controller. That's why we had rumble motors sitting beneath the surface to provide that vibration. And we did this in tune with the games. So the game mechanism, as they immerse themselves in playing the game, we had to send contextually relevant feedback to their hands to reinforce it. And there's published literature in this area in serious games about the fact that you can reinforce gameplay with mechanical vibration. But because we designed all of our games, which was the harder path to take, it meant we could have complete control. And that meant we could record all game sessions, and that was important for my trial. It meant that we could randomize and influence all of the game activity as well, which meant that the games could generate random content every time a new game was played. And using smart sensors, as I talked about before, we could actually have this idea of what occupational therapists refer to as forced by manual use, so having both hands always on the controller. So in terms of what the gaming system looked like, I'll just slowly introduce it to you before I show you a video of some of the games that we developed. So this is the main menu screen that you see as soon as you log in. So this is actually the second screen. The main screen is just the login screen. On the left-hand side, you can see there's 15 cubes, and those cubes each have a name, and each of those cubes is wrapped in artwork, which is part of that game. So for example, if you look at the first row and look at the first cube, which is on a bit of an angle, it's called A Bridge Too Far. That's the artwork from that game. And if you look onto the right-hand side now, you'll see that that smartphone on the right-hand side is showing you a video or a screenshot from that particular game. So we were using a couple of strategies here. First of all, we were showing the children all the games they could play, because every one of those cubes was a game. Secondly, the smartphone on the right-hand side, we would deliberately show video from different time points in the game. So maybe the first level and the fifth level and maybe one of the levels down further in the game to hopefully draw them into playing that game because they hadn't seen that particular scenario before. The high score tables, which are underneath the title on the right hand side, which say David, because I was playing the game, and then the guest. This was really interesting. We used this high score table deliberately because if the child's name didn't appear here, like mine does, if it was guest, then that was that particular child's brother or sister or mum or dad or friend next door who was playing the game and who'd achieved a higher score than they did. So it was actually a very good motivating pull to get the child to come back onto the gaming system to ensure that their name was on top of the high score table, and this said Luke or Sally or whatever the child's name was. So this was a very subtle but very good way to get the children to get back on the gaming system and play it so their name was top of the leaderboard, so to speak. I'll just click through to the next slide and show you some screenshots and some movies of the games, and I'll give you a commentary over the top. So here is our gaming system, and this is one of the first games. This is A Bridge Too Far. So the idea here is you collect the coins and the jewels and jump over the gaps. This is probably a more advanced game. It's called Biplane 1922, and you have to fly through the English countryside and fly through barns. This is Racing Maniac, and you have to avoid the cars on the road but collect items at the same time. One of our other driving games, you navigate your way through different worlds and collect objects to get to the next level. One of our games targeted more at younger children, you move through the food chain by eating other objects in the ocean. And of course, no catalogue is complete without a dress-up game. So here is our dress-up game where you dress up characters for a certain activity. I'll play that again because it goes through fairly fast. So just from the top, we're making a selection from the menu, and here's A Bridge Too Far. So all of these games are all controlled just with a joystick once you're in the game. So you just move the character or the avatar around the screen without any buttons. Here comes Driving Maniac again. So this game actually has artificial intelligence built into it, and the cars start changing lanes around you as you get further into the game. Collecting objects and going to the next level. Then Marine Life. And then our dress-up game, so choosing hairstyles and hair colours. And if there's interest, I actually have a longer video I can show at the end which will show you all of the games we've made. It goes for about 2.5 or 3 minutes. So some of the features of the system. First of all, it's got this idea of smart sensors which can detect hand positions, so both hands, but more importantly, the more involved hand is always engaged on the controller. And that more involved hand is actually receiving the vibration from the motors underneath the controller as well. Because we've made the games ourselves, we can track and log every action and every event within the game, which was an important aspect of what we were doing. We can customize almost every aspect of the game, and I'll talk to you about how we did that. But one of the important messages I want to convey today is that we weren't just sending a vibration signal to the child's hands at a given point. It was a varying level of vibration, from a very fine vibration, so a very small amount of vibration, to a large amount of vibration. So the level or the magnitude of the vibration varied, as did the duration. So sometimes it was half a second and sometimes it was a couple of seconds. The other thing was we designed our games so they would generate random content. Now what that means is if you were to play any two games back to back, then the location of the collectibles within that game, where you'd start in that game, and how that game would actually play out would be randomized every time you played it. So even if you played the same game 4 times in a row, it wouldn't actually be the same game because the track would change or the world would change, and where you collected items within that world would change. And we did this to hopefully generate the ability for the child to come back and play it again because it was new and they were discovering new things each time. So this next slide I'm going to show you is a teenage boy with cerebral palsy who was playing and interacting with our gaming system on World Cerebral Palsy Day in October last year. So here he is. He's using Orbi to play Squirrel. So in Squirrel you run up a never-ending sequoia tree. You might be able to hear some of the sounds of the game in the background. So he has to avoid the tree knots and avoid the branches but collect nuts and coins. I'll play this a couple of times. So let me play this again. So whether you're watching the screen and watching the game or watching him using Orbi on the table, you can see the movements that are being encouraged and how he's having his hands sitting on top of the Orbi controller. Now the big stress in this game is that the better you go in the game, the more you achieve, the faster the character goes. So his squirrel will go faster and faster if he keeps achieving. Okay, now right at the very end there, you can see the prompt on the screen. He received this pop-up. And the reason he received this pop-up is because one of his hands slipped off the sensor cover, and so it was telling him that he had to put his hands back on the controller. So this is the prompt or the pop-up that every child will get if, in this case, you can see there's two white arrows, so both hands are off the controller, but it will actually be able to sense if it's the left or the right, or the left and the right together, and it will instruct you on the screen to put your hands back on so you can continue the game. So this is as annoying as someone sitting behind you with the remote control for the DVD player pushing pause at random intervals while you're trying to watch a movie. If their hands are not covering those smart sensors, the game pauses. But as soon as they cover the sensors again, they get counted back into the game, 3, 2, 1, and they can start playing the game again, and they haven't lost any ground as to where they were. So during the randomized control trial for my PhD, we had this deployed to 18 homes here in Adelaide, and this is just showing you some of the photos that either I took or some of the parents took and sent back to me. So I think in about 15 or 16 of those setups in the home, it was usually in what we call the heart of the home. So the dining room table was used, and you can see they're sitting here on the right-hand side. This young participant has got the laptop computer sitting on just a box lid, just to raise it up a little bit so that they can see over the top of the Orbi controller to play the game. And on the left-hand side, it's sitting on the dining room table, and that particular participant is playing that game that I showed you already, A Bridge Too Far. Okay, so in terms of some of the results, what we identified with the first 9 children that went through the trial, just to orientate you to this graph, the bottom is showing you the participants or the subjects. The left-hand side scale is showing you how many minutes they played the computer gaming system. The 2 bars that you can see for each number, the blue bar is the child that we gave the system to, and the red bar is the guest profile. So this is how much their mother or father or siblings or next door neighbours played the gaming system. So firstly, you can see that in almost all circumstances, the child that we gave the gaming system to played the game the most, except for subject 9, where their sibling or siblings played it more. As I'm indicating with the large bold number on the left-hand side and the orange dotted line, the average for all of those children, so just looking at the child now, for playing it was 267 minutes, which was just about 44 to 45 minutes a week because they had the system for 6 weeks. So when I first got the first batch of data back in, I didn't think that they were playing the gaming system for long enough. I wanted them to be playing it for probably 20 to 30 minutes a day and not 45 minutes in a week. But as I said earlier, as a parent, I recognise that family life is fairly busy. School, after school, extracurricular activities do take up time, but I still did want them to play it for longer. So what we did was we implemented a very common strategy, and usually this is where I look around the room to see who might be looking up at me about with the next thing I'm about to say. But if you've ever played Candy Crush or Angry Birds or any of those other games, you'll know that a very common ploy to get people playing games is actually the reward system. So if you play games for a certain amount of time, you get rewarded by getting to the next level or the next game. So we decided to do the same thing with our gaming system. So now I'm showing you the menu system that I showed you before, but you can hopefully see that on the left-hand side, not all of those cubes are brightly coloured. In fact, only 5 of the brightly coloured cubes are there, and the rest of them are greyed out. So what we did was we said to the children, you can start with 5 games, and as you keep playing the system for longer and longer, every half an hour a new game will be released. And so it was this sort of risk, well not risk and reward, but they had to play the gaming system to earn the games. So the idea was that maybe giving them 15 games up front with no reason just giving it to them was probably not a good strategy, but actually giving them only 5 and making them earn the games by playing them was probably a better strategy. So if they try and play a game which is grayed out, then they'll receive a prompt like this. So in this instance, we've tried to access this game up here called A Bridge Too Far, and it's saying we can't, the game is locked, but if you keep playing for 3 hours and 56 minutes, well then you can unlock that game. So every half an hour a new game was released, and the time was always relative to the person we gave the controller to or the gaming system to, so it was tagged to the subject. And when they did unlock a game, they would receive this prompt. So they get a big congratulations message saying, congratulations, you've unlocked a new game, this is the game that you've unlocked, and next time they go to the menu screen, they'll actually see that game in the menu and they can play it. Now, what did this do for my trial? Given that the first 9 children went through the trial and the average was 267 minutes. Well, what it did, if you look at the right-hand side, was actually made the children engage and play the system a lot more. It's probably not fair and it's not statistically accurate to talk about averages because, as you can see, we had some very, what we call power users use the gaming system in the next half, the next 9 subjects. But if we talk about median, so the median values with the new and the sort of play to earn catalogue, well, the median person used the gaming system for almost 2 hours extra in that 6 weeks and for at least 3 days more. And the average amount of time that the system was used for was now 488 minutes instead of 267. So you could say that we did achieve what we wanted to, which was to get them to play the gaming system for more or for longer by using what we call an incentivized catalogue. But again, just reporting on medians and not averages here. We also asked the families and the children to rate the gaming system. So we asked them to score out of 10. And we did this for both the haptic version and the non-haptic version because some children received active feedback on their hands and some didn't. And we did this for the old system and for the new system. So you can see from this particular graph I'm showing here, the system rating, and you can see the numbers are actually quite small, so just 4 children in the first and then 5 in the second. But while there's no statistical significant difference between these 2 groups, you can see the large error bars, they tended to favour the haptic version of the catalogue compared to the non-haptic version, but it's not a statistically significant result. We then asked them to rate the systems again with the new catalogue. And you can see that the highest rating system, which is the yellow vertical column in this particular graph, is the haptic new system. So when they had to actually play and earn games, they valued that system more than the other systems. And they preferred the system which gave mechanical feedback or vibration feedback to their hand. Just to add again that there is no statistically significant difference between these results. So statistically, it's not a statistically significant result, but you can see where the trend is going in terms of how we might develop and progress the gaming system into the future, knowing that the haptic system is rated higher and the fact that if you earn the games, you tend to play it for longer. In terms of parent feedback, we had a number of parents who would either talk when I picked up the system or send me information via an email about what they thought. And I just wanted to conclude with some of the feedback that we received from the parents in terms of the overall system. So this particular parent was saying that he is showing his older sister what to do and explaining how to do some of the games. The 2 of them together are interacting beautifully, sharing, discussing and encouraging each other, and then of course trying to beat each other's score. So the general feedback from this particular parent was that her son and her daughter were actually playing, engaging, but now competing using the gaming system probably in a manner that they weren't able to compete on a level playing field before, because the Orbit gaming system provided this level playing ground. It provided a controller that was accessible with games that required limited input, so the controller and the software working together, and it meant that anybody could do it. And for the first time, her son was probably actually able to beat his sister in a same game where he's not being disadvantaged because he lacks the coordination and finger control he might for other systems. She also noted that he has learned considerable control and how much pressure and force to use on each game. So this meant that he was effectively using the controller in a very controlled way to work out exactly how responsive each game was. Some games were very responsive, some games required wide sweeping movements, so a full left or a full right to turn left or right rather than just a small movement. And he was able to actually work out the nuance of every game in terms of how sensitive it was, how the car would respond to movements, because we actually program the games differently from that perspective, and also exactly how much he had to cover that little window with the smart sensor. So he worked out exactly where he could or couldn't put his hand to make the game work the whole time. Two other things I'll just highlight as well. I had a parent tell me that her son became more verbal because of the gaming system, and what that was the child we gave the gaming system to was non-verbal, and he was achieving very well within the gaming system, and his able-bodied sister was not able to get to the same level in some of the games as he was, so he was coaching and instructing her in terms of where to go, what bonuses to collect, and he was giving her game strategy. So he started to talk more because of the gaming system. And we had another father report that his son was having more conversations about cerebral palsy to people who would come to the home and visit, because the gaming system was set up on the kitchen table. People would come in and see it. He was very proud of the gaming system, and because it had that really nice form to it, he would then start talking to people about what cerebral palsy was, how it affected him, why he was doing the trial with those people from Flinders University, and how he was enjoying it. So as his father said, it helped him start that conversation about cerebral palsy and disability and what it meant for him. If we now look at some of the statistical results from the randomized controlled trial, just for completeness, we did a number of measures for sensory function for these children. So you can see here with the dashed bullet point where we're looking at a test of registration with monofilaments for the finger and thumb. The Aztec is a test of discrimination, so it has grooves that are of different widths and that are spaced differently. Proprioception is with the thumb. Stereognosis is asking the child to identify an object when it's placed in their hand and they have a blindfold on, so they manipulate it in their hand and tell you that it's a matchbox car or a paperclip or a pen. And the Jebsen-Taylor test of hand function is a measure of motor function and hand performance using a series of timed tasks. So what we identified with the analysis was that there was no statistical significant difference between the groups in the trial for my PhD. And what this means is that we had a group which we call Group A, which got the gaming system with the haptic vibration turned on, and we had a group called Group B, which had the same gaming system, but we just turned the vibration motors off. So in essence, we were trying to distill the influence of vibration feedback to the children, to their more involved hands. And so we had no difference between our sensory measures there for our 18 children. But what we were able to understand, looking through the detail of the stats, was that Group A improved their proprioception, stereognosis and Jebsen scores, and Group B improved their proprioception and Jebsen scores, so not their stereognosis scores. Now, these didn't achieve statistical significance, but that's because we were underpowered with our study. So we only had 18 children participate in the study over the 18 months that we had the recruitment window open for. And we believe, using this as a pilot trial, that we probably need something like 54 or 55 children to drive a statistically significant result. But the trend is that there are improvements occurring in the background, but just not to a statistically significant result. But what we did identify is that for all of the children in the trial, so irrespective of their group, either Group A or Group B, all of them actually recorded a statistically significant difference for their Jebsen-Taylor scores for their more involved or non-dominant hand between two of our measures. First of all, it was the baseline measure, and then the follow-up, so the 6-week post-trial measure. So this is really interesting. We believe at this point that one of the reasons, or maybe the driving force behind this statistically significant result for the more involved hand, and of course that's the hand that you want to improve function in, and you can see the level of significance there, is because of the aspect of the smart sensors, the force by manual use. So the controller and the games are probably achieving the immersion and the buy-in that we want, and hence they're trying to and really keen to keep playing, and so the sensors are sort of keeping them honest in that respect, and it's making their hands stay on the controller, and so we believe this is a driver for this result here. So in conclusion, the randomized controlled trial, the pilot trial from our PhD for what we call the Orbit gaming system, because Orbit combines the Orbi controller and an aspect of IT, which is the laptop. We deployed it safely to 18 families here with very minimal support. I dropped it off, gave an overview for about 15 or 20 minutes and left it with families for 6 weeks and then collected it afterwards. So we identified it as being safe and robust, very intuitive, easy to use, well liked and accepted. It demonstrated that it was a home-based solution, so they didn't need to come into a clinic or to the hospital. We could just deploy it to the home, and we made sure that it was independently accessible, picking up on the universal design philosophy that these children, when they wanted to game, they could just go and do it themselves and weren't relying on others to set it up for them. We had a number of parents report increased socialisation amongst the siblings, so between the child that we gave it to, but it was a deliberate strategy to give it to the child and their family. So whenever I did a training session, I had the child and their parents and any siblings there so they could all understand how to use it and go from there. We do require further research to really look at the type 2 error that we've encountered here, which is a lack of power, and we know that we just need to recruit more children to another study to try and see if we can look at some of the drivers or trends that we're seeing to get a statistically significant result for somatosensory impairment. And because of the interest in the system, we're actually looking for possible commercial and research partners to try and move this further along. So that was how the pilot trial ended up. I just want to conclude with a quote from a very recent publication by Piazza and colleagues from just a couple of months ago, where they did a quality of life rating for children, and they assessed both the children and their parents for what they rated was an important aspect in these children's lives. And interestingly, the children rated playing video games as the second most important quality of life rating for them, so their self-identified quality of life rating. The most important quality of life ratings for children was actually using the remote control, so they could control the TV or the DVD player, and video gaming was second. Now both of those two were actually statistically significant different from what their parents rated as the most important quality of life rating for children. So what the children wanted to do and what they saw as a quality of life measure was quite different to what their parents wanted. But they concluded that the interest in video games can be turned into a positive. And I suppose that's the underlying essence of what we've done here by developing the Orbit gaming system and then having them see it as a motivating and engaging tool or opportunity to interact. I'd just like to conclude with by acknowledging first of all Flinders University, my faculty and my school for the support, but the fact that we couldn't have done this trial, we couldn't have recruited a group of children from the South Australian Cerebral Palsy Register and then conducted our randomised controlled trial if it wasn't for the groups that I'm acknowledging here, so the Women's and Children's Hospital Foundation and the Channel 7 Children's Research Foundation here in Adelaide. I'd like to acknowledge all of my fantastic colleagues, so my supervisors, the people who work with me from the gaming and the controller side. Most notably, all the families and the children involved in our study. We had a number of schools involved that were giving us feedback on our games and giving us critique as to what was happening and what they'd like to see in a game, and of course the wonderful staff at the South Australian Cerebral Palsy Register as well. So a couple of last images and some contact details if you'd like to follow up and contact me after this presentation. So you can see the Orbi controller in front of the Orbit gaming system there from another angle, and you can just see where the smart sensors are positioned here in the oval pad and the gaming system in the background. And then this is actually my young son Thomas when he was only 3.5 or 4 using the gaming system for a photo for the State Department here in South Australia. So thank you very much for your attention. I must say it's quite a different experience to sit here and talk to my PC and not have a live audience look at me and nod, or look at me with a quiz look if I haven't explained something correctly. But thank you very much for your attention, and I look forward to any comments and feedback that you might have. Thank you.
Thank you, David. Great presentation. I've got a number of queries and questions that have come in during your presentation. Firstly, your offer of playing a short video is something that people want to take up. I guess perhaps we can talk to you offline about whether we can record that and post it alongside this webinar for people who want to access it.
Sure. So those two videos that I used in my presentation are actually in that Dropbox folder, so you can post or host those two videos. And if you'd like me to do a similar thing and host or try and connect you with the larger video which shows you all of the games, then I'm happy to do that as well.
Terrific. I've got a couple of questions here that I'll kick off with. Nola, who's a service provider in a regional area, asked, she picked up on your point about your pilot needing more numbers, and perhaps you are looking to engage with service providers to do extra research and to trial it. So she asked,
Yes.
how could service providers get involved and help you get the numbers required to do more trials?
Look, excellent question, Nola. At the moment, my focus is trying to complete my PhD in terms of writing the thesis up and getting that submitted, because I need to do that, and the clock is ticking. And for anyone out there who's gone through the PhD process, you'll understand what I mean when I say the clock is ticking and things have to move along. But I am definitely interested to know if there are people who would like to be a satellite group for a possible larger trial. We have a number of controllers that we made when we had the grant, and we can host the catalog, the gaming system, on a server so people can access it and then load it onto a machine. And the best way to do this would be to effectively use this exactly the same protocol that I use for my RCT, so that we can really compare results, so the same measures and the same time points, so the same length of time and things like that. That's something I'm going to have to talk to the Institute here about, how quickly or when we can do that. But I suppose the first interest is if people wanted to contact me and register their interest, I at least know who we can turn to do a larger trial.
Terrific. I've got two questions that I think are interrelated here. One from Julia, who's with a large service provider, and one from Marissa, who is in a remote rural area. So I'll combine, if that's okay, Julia and Marissa, I'm going to combine your questions a bit together. Julia asks, it's such a fantastic project and piece of equipment that would obviously really enrich and assist many children and adults alike. When do you think it will be commercially available? And Marissa asks the next question to that, which is, fantastic piece of equipment, and how much would it cost?
Look, first of all, thank you very much, Marissa and Julia. Is that right?
Yeah.
I might have got the names wrong. I apologise there. Thank you very much for the comments. That's very nice to hear. Probably one of the reasons why I haven't submitted my PhD at this point in time is because we have really been trying to actively engage with a commercial partner. And so I presented on this research in Italy and the US a couple of years ago. I actually pitched the whole system to AbleNet from Minneapolis in Minnesota for looking at taking it on as something, because they're a very large assistive technology distributor, and we've been engaging with people in Singapore and New Zealand and Canada in terms of a company that might want to or be in a position to pick up the technology and put it under their umbrella and distribute it. The long and the short of that is that we haven't found a company who's willing to invest or to move the idea forward, which is both disappointing, but at the same time I do understand where they're coming from when they explain their rationale. But just recently, in the last couple of months, we have been engaging with another company and an individual here in South Australia who seems very, very keen on the idea And that is because we're now talking about it as more than just a device to play computer games, and then, as the first person noted, more than just for children. And so we're starting to talk about it as an accessible interface for possibly just getting access to your computer or your remote control for your TV or some of the things you like to control on your home. It's just that accessible interface. And we've decided to take a new tack on where we go with the gaming system overall. So there's lots of work been going on in the background, and it's still going on in the background at the moment. Our optimal solution is to partner with someone who can take it to market with us or for us, but we're still trying to identify who that person or who that group might be. Ideally, we'd like to get the controller on the market for under $300. We've had a look at lots of different ways of manufacturing it, because we just 3D printed it for my trial because that was the most economical way of doing it. But in terms of tooling up and designing it for manufacture and distributing it, we've looked at some numbers, looked at different techniques. We've engaged a design for manufacture company here in Adelaide, and we're trying to really get it out there, like I said, for hopefully under $300. So there's lots of work going in the background, but because we haven't got a specific group I can talk about or name or know what some of those timelines might be, I can't be as, I suppose, specific in my response.
Okay, thanks David. That's great information. I've got a question from Harry, and Harry's has indicated that he's a policymaker, so interesting to have you on board, Harry. And your question, I guess, is about the NDIS, and with the NDIS on the horizon and its focus on investing $1 billion into assistive technology. It would be fantastic if there was something like this available for deployment when the NDIS is fully rolled out. Is that your aim, David?
Yes, as it turns out, my former director, who I used to work with at Navita Children's Services, is part of the innovation agenda in Geelong with the NDIS, and so I've had some conversations on the side. I definitely agree with where Harry's coming from, that the NDIS is probably going to provide the framework that if someone would like to access a device like this, well, then I think the funding is going to be there for them to be able to do so. So whereas pre-NDIS it might have been difficult, I think the NDIS environment is going to be more receptive and assisting in that process. So I do agree. What I'm not 100% certain of with what I've read or understood is just possibly under what framework, maybe what mechanism, or what the process might be if someone would like an Orbi gaming system through the NDIS. And so if Harry or others know what that might look like or what that might be, I'd love to know. But I definitely think it's a more positive environment, I agree.
Terrific. We're nearly out of time, David, and I think any other questions that we've got here we might need to take offline. But I'd just like to formally thank those people who asked questions, and to thank you today for providing such an in-depth presentation on this topic. The webinar will be posted on our Community Care Smart Assistive Technology Collaborative, and we'd be keen to have you, if you haven't already registered or all your staff and colleagues, to promote this service. It is a free service provided by the Queensland Government, but with an aim to engage nationally and internationally. We've got a couple of upcoming webinars coming up, and you'll see on your screen now our next one in June is scheduled for next week, and we're going to talk about a range of smart technologies to enable and enhance remote working. In July we've got a number of webinars coming up, and the topics include smart homes, smart cities and driverless vehicles. I'd like to particularly acknowledge the project team that has brought this webinar together today, and also our expert reference group. Members represent nationally interest areas, and they contribute to the development of our platform. I'd equally like to thank the Queensland Government, who's provided some funding and support for this project, And again, thank you, David, for today's presentation. Very valuable research. Great to see it's Australian-based, and great to see that you're looking at bringing that important research to market. So thank you, David, again for your time today. If you want any more information on our project, contact the Smart Assistive Technology Collaborative Project team at the email on your screen now, being sat@communityresourcing.com.au. Thank you everyone for your attendance today, and I look forward to having you involved in future webinars and activities of the collaborative.